Hi everyone, in this video what I'm going to cover is rotational motion. So I'm assuming at this point you had some background in kinematics, and for the most part we did translational kinematics. The word translational just means linear and straight lines. So now we're going to shift gears and talk about things that rotate, okay? And what I mean by rotate is now you have, I don't have an object to do, I don't know, I'm going to use my calculator. Okay, we have an object now. And instead of it moving in a linear fashion in like one direction, or this is 1D, you know, and a line is 1D, 2D is at an angle, right? 3D is if I move it forward and backwards like this. We study kinematics to kind of model that. Now, we didn't really study 3D, but that's okay. Now we're going to take objects and we're going to rotate them. And we're going to find that we can model them the same way as translational kinematics. But we have a few changes to make. So when an object rotates, we have an imaginary line that goes through this called the axis. You might have heard that before. And the object rotates about this imaginary line called the axis. Now, of course, my calculator is not the best example, but you can see that. Now, I rotated with the axis right here, but notice that I can rotate this in many different ways, right? I could rotate with the axis along here, and I can rotate it this way. I can actually put the axis here and have it rotate this way like a fan blade, right? I can have it rotate on this side and rotate kind of like this. It's kind of hard to see a little bit, but point being is there's many ways I could put the axis here and I could rotate it like this. So you can already see how complicated it can get just by changing the axis of rotation. So when we study rotational motion, this whole point in this whole lesson is we're going to model the motion of this. So we're going to look at motion specifically. So we're going to look at angular distance, how much, I'll say it in this way, how many degrees we cover because we're going in a circle-like motion. We're going to look at distance as angles instead of length. We're going to look at rotation and how many spins do I make. So instead of how fast, how much distance per time, I'm looking at how many spins I make or how much angle I make per time. And then, of course, we have angular acceleration, how much we're changing our spin, right? So I can speed up and slow down, which would be angular acceleration. So I'm going to teach you basically the kinematics for rotation and define some new terms and some things we got to watch out for in physics. I guess I'll do it in presentation mode. That looks a little better. Okay, so again, this is just a brief definition of rotational versus translational. Now, translational is just a really big word for linear, so I'm going to use it just to use it. A lot of physics terms and books and concepts use the word translational, but just know that's linear. So here is the difference, right? So I try to model this with these little diagrams here. Rotation is you have this imaginary axis, so that's what this dotted line is, and the object moves about that axis. That is rotation. So anytime I model this in class or with problems, angular motion will be a curved arrow because we're spinning, okay? When we're looking at translational velocity, it will be a straight arrow, and I hope that makes sense. So, of course, we're going to have mass that's going to be outside or inside this axis of rotation, so we're going to use the concept of radius to kind of help us with that. So, generally when we talk about rotating objects, you're going to have some sort of radius r. Now, when we say pure rotation, you're going to see the terms without slipping. So if you imagine, if I took this object, right, this is not a circular object, but if I allow this to go along an incline, it would fall like this, right? It's going to fall, I'll do it up here, it's going to fall straight down. This would be sliding or slipping. Now, rotating would be exactly what you might imagine. Of course, this is not the best example. I need a ball, actually. But we're not going to slip, which means it doesn't catch and slide, so it's only rotation. Now, in real life, you could have a combination of both rolling and slipping, just because of the nature of the friction on the system, but we're going to just talk about just rotating. There's no slipping, there's no catching of that. So that's why you might see pure rotation without slipping. Then you have pure translation, again, slipping or sliding. So any of those, the things that we've studied, so if you take a block on an incline and you allow it to go down, that's pure translational. There's no rotation in a block sliding down an incline. There might be rotation in a ball down an incline, but not in a block. So just to reiterate, so translational means linear motion, no rotation. Rotation is a motion fixed around axis, but we can have both types of motion. Your most common example will be a ball on a ramp, because a ball can both move. If I draw a diagram really quickly of this, let me actually go over here for a quick second. We could have this case. This is a terrible drawing, I'm so sorry. Here's an incline, right? We can have a ball on this incline, and then it can roll, right? So it'd have angular velocity, but it also moves down the incline with a linear case. So this has two types of rotation. Not rotation, but two types of motion. Versus if I had a block, this will not rotate. It will just move linearly down an incline. Now something with just, one type. So this is just linear. This is both linear and rotational. Something with just rotational could be, for example, a pulley. And let's say I hang some masses on it, where we have just rotation, right? But the pulley isn't moving forward or backward, so the velocity of the pulley linearly is technically of the pulley itself. We'll just say that for now, just the pulley. It's not moving two ways, it's zero. So you can have just rotational, like an object staying stationary. A stationary object spinning, basically. Now, if we talk about places on this, that definition will change, but for the most part, we'll just go with this, just to show you some examples of the different types of motions that can exist. So naturally, what we're going to study is the rotational at this point. We're just going to model the motion. And just like we have forces and energy and momentum, we're going to have rotational force, we're going to have rotational energy, and we're going to have rotational momentum. Now the good news is it's very similar to what we learned because all the rules of motion apply to rotation. What the difference is now we have to consider radius for all these cases, and we're going to redefine some of our terms to represent rotation. So I'm actually going to show you the endpoint just to show you where we're going, but when we're modeling linear kinematics, so if we look at this, final velocity is equal to initial velocity plus at, delta x is equal to vit plus 1/2 at squared, etc. These are our kinematics. Turns out that our rotational motion kinematic equations are essentially identical, but if you notice, we're now going to redefine rotational motion with different symbols, right? So you can even, just by looking at this, you can kind of figure out where we're going. So omega here represents a final rotational velocity. This is initial rotational velocity. This represents angular acceleration, and t is the same in both cases because time is in the same, you're covering the same time regardless of your motion. So time is the same symbol in these two cases. So if you notice, all we're doing is replacing these rotational symbols with the linear kinematics. And then if you notice here, instead of d, we have angle. So like I said, we're going to look at how much we're spinning, how many angles, how many degrees did we go versus, how far do we go in a linear sense. So when using rotation, replace the linear variable with rotational variable. The kinematics are the same. So here are the definitions of each of those things. And what makes it simple for me is just treating it like kinematics. I just find the same variables I would for kinematics and just replace it with this. That to me is the easiest way to approach this. So theta here represents angular displacement measured in a unit called radians. So I'll define radians in the next slide, but we're not, although we can measure angle in degrees, which we mostly do, when we're talking about motion, specifically rotational kinematics, we're going to measure everything in radians. So if they give you revolutions or degrees, you must convert. So I'll show you how to do that. Same thing, angular velocity is distance over time, but instead of linear distance, we have radial distance, so radians per second. And then angular acceleration, as you might imagine, is distance per time squared, and that's why it's radians per second squared. So similar, except we changed our distance to radians. Time is both the same. And look at the parallels with that. This looks like A, this looks like V. I mean, these don't really look the same, but you get the idea. So what do these rotational quantities mean? So this is just to give you a visual of what theta represents. So if we're rotating about a fixed point O right here, and we're watching this line, for example, move from point X to point P, I'll call this, we have moved a radial distance of a theta here. So that's what theta actually represents. Now we can get the physical linear curved distance through this relationship, but let me tell you, you're probably not going to need to do that. But if you notice, if you want to find the arc right here, you would do the radius times the angle. That's the physical measurement. But we don't want to, we can measure this, but this is not something that's going to be focused on. What's more important is understanding what this represents here. So it measures the angle. We always start at the positive x-axis and move counterclockwise, okay? So this is the positive direction. Oops, my fault. So the angles be measured in radians. So if you have the angle measurement, there are 360 degrees in 2 pi radians. So 2 pi represents the full complete circle. 1 revolution is a full circle, so 360 degrees, which is 2 pi radians. So this is slightly out of order, but that's okay. So just a quick distinction between rotation and revolution. Rotation is when the axis is inside the object. So notice in this fan blade example, right? The fan blades are rotating about this imaginary axis, which is inside the object. So when we do that, we use rotational models. So everything that I'm teaching you now. When you have something that revolves, like this, that's when we use our circular motion models, if you notice. Like the Earth revolves around the sun. Now the Earth is outside the axis, so if you notice here, right? See, the axis is inside the sun, not the Earth. So this specific case is actually a revolution because we're going around an outside point. But to be technical, right, the Earth actually does both. It rotates 24 hours on its own axis, but it revolves around the Earth 365 days. So here's an object that has both rotation and revolution. But coming back to this concept, the theta, right? So this animation here I find actually incredibly useful because I didn't understand what a radian was until I saw this animation on the right. So I'm going to talk a little bit and then I'll focus back on that. But these are all the conversions that you must do in this unit. I believe they're also on your equation sheet, but we're going to measure the angle in radians. If you have it in degrees, you can convert with the following. But this actually animation shows you where the radian comes from. 1 radian is essentially how long a radius is. Radian, radius, right? So watch the beginning of this. Sorry, we're just waiting for it to reset. So here's our circle. We're going to sweep out a circle. So this represents radius. If we put this curve onto here, the angle that we measure is 1 radian, because that's the angle right here that makes this curve, 1 radius. So notice that we need 1, 2, 3, and a little extra piece to make a half a circle. So that's the 3.14. That's pi radians. And then we need another pi radians to make a full circle. So that's what 2 pi radians actually represents, which is why we can say 1 revolution is 2 pi radians, which is also why we could say 360 degrees is 2 pi radians. Another thing to be aware of in physics problems is they like to write revolutions per minute, so RPMs. So 1 revolution per minute. So just be aware of that. Now, naturally, we want to get out of revolutions and go to radians, and then we're going to want to get out of minutes and go into seconds. So, one conversion we'll have to do is going, for example, 50 radians per minute to radians per second, because we always want to be in radians per second. So let me just quickly demonstrate that. So 50 revolutions per minute. And I want to go into radians per second. So here's how you would do such a thing. So 50, I like to write it like this. And when you have a double conversion, notice we're both converting the top and the bottom. It doesn't matter which one you want to do first, so long as you cancel out the terms that you need. So I'm going to do revolutions first. I want to make sure revolutions cancel out, so I'm going to put my revolution on the bottom. And I know that in one revolution, there's going to be 2 pi radians. I got that from the previous page. Revolutions cancel, which leaves me with radians in the end, which is what I want. Times, for every 1 minute, minute goes on top because I want the minutes to cancel. There are 60 seconds. So if I were to calculate this, 50 times 2 times pi, you can use the pi button or 3.14. I'm going to just do it out in steps. So I have right now 314 radians divided by 60 seconds. And that's because I have 1 here and 60. Now I'm just going to go ahead and do that. So that is now equivalent to 5.23, this is radians per second. This is the unit we want to always be in, like this. And since it's a radians per second, that's a angular speed. So basically what this says, it does 5.23 radians in 1 second. So if you remember, 2 pi radians is 1 circle, right? So 2 times pi gives us about, so every time you do 6.28 radians, that's 1 circle. So what this number means basically is this object rotated, if this is the axis of rotation, almost a circle, right? So it's about here. So what, from here to here. So almost, this is not super drawn to scale, but the point is 5.23 is a little less than 6. So it didn't go a complete circle, but it almost makes a circle in 1 second. And that's what this basically means. So how much angle change per time, seconds like this. So this is a conversion you'll get comfortable with because it's very common in the physics. In fact, most of your physics problems online will have you convert something like 50 revolutions per minute, and you'll have to go into radians per second. Okay, so let's hop back into this. Okay, so these are just a couple of quick questions we can try out so you can see how we're using this right here. So here's a bike wheel. It's made 4.5 revolutions. How many rotations? So for my conversions, I know for every 1 revolution, there are 2 pi radians. So this is a conversion, 4.5 revolutions times in 1 revolution, there's 2 pi radians. The revolutions cancel and I can get radians, so 4.5 times 2 times 3.14. I'm using 3.14, but again, you can use your pi button, which is totally fine. It gets 28.26 radians. So just taking these revolutions and putting it into radians. Now, if you remember that magic number 6, right? So this is doing, 6 is 1 full circle. So this does a couple circles, right? I mean, if I divide this by 6, I get this roughly goes in, makes 4 circles per second. So that's, well, not per second, sorry. That's just how much it rotated. So it made 4, well, this makes complete sense because that's what that number represents. 4.5 rotations is this many radians. Okay, we can do something like this. Say we have this many radians, how many degrees? So it's another conversion factor. So we can do 3 times 10 to negative 4 radians times I know there are in 1 radian, I'm sorry, in 2 pi radian, there's 360 degrees. So if we want to know how many degrees it is, we're going to do 3e to the negative 4 times 360 divided by 2 divided by pi. 0.0172 degrees, like that. So I'm getting these numbers because I memorized them, but until you do, these are really helpful. 1 revolution is equal to 2 pi radians is equal to 360 degrees. And just know that this is a unit, this is a unit, and this is a unit. So you do need the full 2 pi right here. Can you use 6.28 because that's 2 pi? Absolutely. You can totally do that, and that's totally fine. So just know that this is just notation. Do whatever is easiest for you to understand. Okay. And there's the answers right there. So angular. So angular velocity, like I said, is always represented by a curve because you're counting spins. Basically, how many circles does it make over time? So we can represent the number of circles as angle and then time. So delta theta over delta t is defined as omega. Now remember that 1 full rotation is 2 pi. So we can do 2 pi divided by capital T, which represents represents time for 1 rotation. So remember that this is 1 full rotation. And this is the time for 1 rotation. So essentially what you have here then is you can measure angular velocity with another method, 2 pi over t. So if we know how long it takes to make 1 circle, we can convert that to an angular velocity like this. So these are 2 ways to calculate this. This is actually incredibly helpful if you don't have an angle measurement, right? And you know how long it takes to make a circle. And this one is if you don't have, the time to make 1 circle, you could figure out how much, how many angles, what your angle measurement is, and then figure out the time. So again, just to make a distinction, omega is always going to be a curved arrow, where linear velocity is going to be this v right here. And this is always measured in radians per second, unless of course otherwise specified, but I know specifically on the AP and homework problems you're going to measure in radians. So just some sign convention, we always take counterclockwise as positive because what's happening is we're starting on the positive x-axis and we're measuring our angles this way, which goes against the clock, so counterclockwise. So clockwise will be a negative velocity. Now, depending on the problem, use the sign convention to whatever specifies, but this is the general specified sign convention. So just like you can move forward and backwards in linear velocity, you can move clockwise and counterclockwise. So we represent counterclockwise forward as positive, and then backwards as, clockwise is negative like this. So again, it's an angular velocity, which means we have a vector quantity. So direction is important. So if you notice, when we studied circular motion, we said the linear velocity is 2 pi r over t. And then if you notice that the angular velocity just described as 2 pi. So notice essentially, if I take this piece right here, which is omega, I could write v as omega r. So we can relate linear and angular velocity here through this equation, which is incredibly helpful for energy and momentum. So we won't use this too much right now, but like I said, when we use energy and momentum, it's good to go from linear momentum to angular momentum, or from angular momentum to linear, by using this relationship. So it's a very, very powerful relationship. And notice that all we need to do to convert this from a angular is just add a factor of r. So what happens is we can actually, if I put a point on the circle right here, it's both going to spin, right? It's going to have this omega, but the linear velocity at that point, if I were to allow it to break away from that circle, v right here represents this velocity. So this object does technically have two parts to it. It has an angular piece and a linear piece, depending on what you're looking for on that at that point. So interesting. Imagine yourself on a merry-go-round, or this is like a turnaround, right? So the question is, who's got a faster linear speed or tangential speed? The person sitting in the middle or the person sitting on the outside? And who's got a faster rotational speed? The person sitting in the middle or the person sitting on the outside? So, the answer is, I hope you thought about it, is that they both have the same rotational speed. Because if you notice, if the person sitting here at this point, just close to the middle, point 1 versus point 2, right? How many spins they made? Well, this angle here is the same angle here, even though it's bigger. This angle measurement is the same. I can expand this as long as I want. So the rotational, the change in rotation is the same between 1 and 2. I hope that makes sense to you. So they have the same rotational speed, but v is different. That's because v is r times omega. As r gets bigger, v will get bigger. Why? Because you have to go from point A to point B in the same amount of time, which means you have to go faster, right? It takes, this is a shorter difference here than here to keep your rotational speed. So it turns out, if you watch this, I try to emphasize this in this animation. For all three of these dots to rotate the same time, they all have to get to this point here. But if you notice, the outside dots have to move way faster than the inside dots to keep the rotational speed the same. Now, of course, this animation's not perfect, but you can get the idea. So, some applications, of course, is, when you run track, right? You ever notice that people are staggered in track? Because if you put the person on the outside of this, they will have to run a longer distance, which is not fair. So that's why the people get staggered in track, so that they run the same distance. So, for someone like me, I hate to rotate and move. So if I'm on a merry-go-round, I choose to sit right in the middle, because I'll still rotate, but I won't have this linear speed, so it won't make me as dizzy. So if you sit on the outside, you're going to spin very fast. So if you want the most adventure or most change of motion on the rides, sit on the outside of the circle. For example, the swings. The outside swing is going to move faster than the inside swings. It's going to be more fun. Not for me. I don't like that. I'll go in the middle. Or same thing, the merry-go-round, the horses on the outside are way more fun because they'll go faster. Now, I'm talking about linear speed faster. So that horse will move faster this way, but you're all rotating the same amount because you're on the same disc. In order for you to not rotate the same amount, this disc would have to break up and shift. And as long as the disc is the same, you're all going to have the same rotation. So here is a great, this is usually an AP question, multiple choice. So, it all has to do and relate to, of course, the this equation right here. Linear velocity is r omega. The bigger the r, the bigger the linear velocity. And this is showing that through these pictures right here. So, same thing, we can do angular acceleration, just like linear acceleration. Final omega minus initial over t. Alpha is just the angular measurement. So how much does the speed change? How much you're changing or slowing down, right? So just like linear velocity, the sign directions tells you what's happening. If your initial omega is positive and you're speeding up, then acceleration will be positive because you're going the same direction. So you're going to have it increase that way. and vice versa. I'll let you read these, but the sign conventions for acceleration are identical to that of linear velocities. And that's what this is. The units is radians per second squared. So it turns out that you can actually write acceleration linear as a component of the angular, right? Just like we had earlier. If I want to know the linear acceleration at that point, I can take r times alpha. So alpha is actually not demonstrated here. So alpha would be a curve like this. Don't worry about these two components. Actually, this r right here that we're measuring will be the tangential one. We're not going to look at the radial one. But anyway, point being, this is the most important point here. This is what you need to recall, is that if you want linear acceleration, we'll use this a lot. You can use it by finding the angular acceleration times r, just like this. Also, some other things that are kind of helpful is remember that these are periodic events. So we can write, first of all, we can write omega instead of the way we had it before, if you recall. Omega was 2 pi over period. Now, period, by definition, 1 over period is frequency. So I could rewrite this as 1 over period because that's identical. And then I could replace the 1 over period with an f. So that's where this comes from. Just another way of expressing things. And then if you notice, if you can get omega, you can find f and t because you can make any of these relationships. So frequency is 1 revolution per second. So that's another way we can convert. So if you have a frequency of 50 hertz, it's the same as saying 50 revolutions per second. And that's actually pretty useful information when solving problems. So I'll leave this here as just extra information. Okay, I'm going to stop the video here because I'm going to do the problems separately. So in the next video, I'll do these rotational motion problems.